differential equation, constant coefficients, using the Laplace transform method. So I'm just going to do a few more examples this morning, just to get a bit more familiar with it, and so on. Then, I mean, the rest of the chapter doesn't really go on to any kind of new kind of topics, but just brings in a few more aspects to this procedure of solving differential equations. Bring in a few more different kinds of functions that you might have seen before, bring them into this kind of fold of Laplace transforms, and look at their Laplace transforms and look at how we solve differential equations that feature those new types of functions. So on page 48, we had a kind of 4-step process for solving the ODE. We're going to see some more examples of that now. So the first process, the first step was to take the transform of the whole equation. Just very quickly summarizing these. Transform of the whole equation, and there we need to use the property, the linearity property of the transform, to break down the transform of the whole side of the equation into the sum of the various transforms of the parts of it, the terms. We need to insert any initial conditions about the unknown function that were given in the problem. And then we go about solving that transformed equation, solving it for the unknown, for the transform of the unknown function, which in the language here we're calling y bar. So the original ODE was an equation in the unknown function y, and we're calling the transform of it y bar. So in step 3, we solve the transformed problem, solve it algebraically for the unknown function y bar, and then the final step is taking the inverse transform, going back into the t domain and recovering the function y of t, which is the solution to the original ODE. So we saw an application of that last time, and we're going to see a few more today. So if you look at page 50, the problem we're going to start with is this example 2.9. And this already is showing a slight twist on it. Here we're going to solve a system of ODEs. Okay? So we've got 2 differential equations in 2 unknowns. So there's 2 unknown functions here, the x function and the y function. They're both functions of t. That's kind of implied because we see derivatives of them with respect to t. They're both only first order equations, so they only contain the first derivative. There's no second or higher order derivatives. But sometimes these kind of things are called coupled ODEs. So it's not like you've got one ODE for the x variable and one ODE for the y function. Both of the unknown functions x and y appear in both of the equations. Okay, so they're kind of coupled together or joined together, the 2 equations, because they both feature these unknown functions. So let's see how we can apply the Laplace transform method to this type of problem. Now it's more complicated than the previous examples because it's 2 simultaneous equations. But really, if we just keep our eyes straight, and it's still following those same 4 steps we've just outlined. Okay. So let's have a look at this then. This example 2.9, page 50. Please do stop me as we go through if you need clarification or you're unsure about something I've written or that. Okay, I won't write out the equations again. They're there on page 50. But so 2 equations in x and y, and we've got the initial condition on the y and the x function. Okay. So the first step is to transform both equations. Transform both equations. Okay. We're using a few things here. We're using linearity of the transform. Using linearity, the transform of derivatives property. One of the theorems we proved about what the Laplace transform of the derivative of the function is, or how it relates to the transform of the original function itself. And other results from the table, just kind of remarking here what we're doing. So those other results I'm talking about will be the transforms of any standard functions we see appearing in these equation. So these equations aren't too complicated, so won't be too much of that. Okay, so transforming the first equation. The first equation is dx dt plus 4 dy dt plus 5x equals 3. When we take the transform of that, we'll have, well, we have to just quickly remark that we're going to write x bar for the Laplace transform of the function x and y bar for the Laplace transform of the function y, which is that usual notation. And the transform of the first equation is going to be s times x bar minus x of 0 plus 4 times s y bar minus 4 times y of 0. That's using two instances of the transform of derivatives property. And then we've got plus 5 times x bar, the transform of the function x. And that's equal, well, in the original equation, that's equal to the constant 3. So when you transform 3, you get the function 3 over s. Okay, so that's the first equation there. And then we transform the second one as well. So it's dy dt, so it's going to be s y bar minus the initial value of y, plus 3 times x, so 3x bar, plus y, so that's going to be a plus y bar when you transform it, and then 2t, so that's going to give you 2 over s squared. Okay? Because looking in the table of Laplace transforms, you see that the transform of the function t is 1 over s squared. Okay, that went fine, no problems there. But now we do have these constant terms, this x of 0, y of 0 appearing there, and those are the initial values of these functions, and those have been given to us in the problem. So we can substitute in their values now. So we can, putting in the initial values, we can say so you're going to get the equation s x bar plus 3 plus 4s y bar minus 4 times y of 0, so it's going to be minus 8. And you get plus 5x bar equals 3 over s. Right. And then the second one, we're going to have sy bar minus y of 0, so it's minus 2. Yeah. Oh, sorry. Yeah. S times y bar minus 2 plus 3x bar plus y bar equals 2 over s squared. Right. Yeah. Okay, now we need to tidy these equations up. Let's just keep the x bar and the y bar on the left-hand side and send everything over to the other side. So on the left-hand side, see, multiplying x bar, you've got s plus 5. Multiplying y bar, you've got 4s. And then there's a constant of minus 5 on the left-hand side. So you put that over the other side, it'll become a plus 5. And let's just keep things tidy. Let's put it over the denominator s, so it becomes a 5s over s. And then we can write that as a single fraction. Just taking my pair of equations and just tidying them up a little bit. And the second equation becomes, put the x bars in front, you've got a 3x bar plus sy bar. You have a constant minus 2 on the left-hand side, so we'll put that over the other side. It becomes a plus 2, and then it'll be 2s squared over s squared. Okay. So here's my final set of tidied up transformed equations with the initial values put in. Now at this stage, the next stage I'm going to have to start combining these equations. So I'll just label them as equations A and B, so I can refer easily to them.
Is the S plus 1 y bar?
Could be. Oh yeah. There's a y bar there and the sy bar in front. Yeah. So this is S plus 1. This factor here. Oh, it's messed up my nice clean page. Yeah. Oui. Why does the S have to come first? Let's just call it 1 plus S. Very good. Save me. Okay. Now, so transformed equations. So and they're now algebraic equations. They're no longer differential equations. Okay. So we just see the unknown functions x bar and y bar. There's no derivatives of them or anything. And we seek now to solve this system for x bar and y bar, potentially, to solve them in terms of s, to get expressions for them as functions of s. And we'll do this by a kind of a elimination procedure. Okay. If you had a load of these equations, you'd have to get some systematic kind of matrix reduction type procedure. But when there's just a couple of them, and they're not too complicated, we can just do rescaling the equations and substituting. So let's say I seek to eliminate the variable x bar. So we can get an equation which eliminates x bar, and will solve the system for y bar. Now, how can we do that? There's x bars here, so how can we get rid of them? Well, we could get rid of them by subtracting the equations if the coefficients of x bar were the same. We could arrange that the coefficients of x bar were the same, then subtracting one equation from the other one would eliminate the x bar. Now, the coefficients are not the same, so we have to make them the same. Okay? So we'll need to multiply the first equation by 3 and multiply the second equation by s plus 5. And then the x bars appearing in those will have the same coefficient. Okay. So we'll consider the equation 3 times a minus s plus 5 times b. That make sense? 3 times a minus s plus 5 times b. So that will have the effect of eliminating the x bars. So we'll just be left with, so the 3 times a will give us 12s y bar on the left-hand side, and we'll be subtracting s plus 5 times b, so we'll have minus s plus 1, s plus 5 times b. Then what do we have on the right-hand side? On the right-hand side, we'll have a 9 plus 15s over s squared minus s plus 5 into 2 plus 2s squared, all of it over s squared. Excuse me? B. Oh, that was a figment of my imagination. That is y bar. Sorry. It came from equation B, but sorry, it should be y bar. Thank you. Okay, so we've succeeded in eliminating the x bar. We've now got an equation which only consists of y bar. Still a bit messy at the moment, but in principle this should be solvable. So we should be able to just proceed now, simplify the right-hand side, collect together terms on the left-hand side, and just find the equation y bar. Okay. So we can do that. On the left-hand side, well, we need to multiply out these brackets. So everything is multiplying y bar, and it's going to be minus s squared. You're going to get minus 6s in here, but you've also got plus 12s, so that's going to give you plus 6s. And then you get a constant 5 from there. It's got a minus sign, so it's minus 5. That's on the left-hand side. Now, I might want to, normally I'd prefer to see that as s squared minus 6s plus 5. So I might want to multiply across by minus 1 in a moment, just to simplify matters. That's on the left-hand side. On the right-hand side, well, they're both over s squared, so I should be able to get this all over s squared. So just need to multiply out these brackets here. So you're going to get a minus 3s cubed. No, sorry, minus 2s cubed. Yep.
9 plus 15.
Yep. Merci. Thank you. 9 plus 15s. That's only over s. So yeah, okay, so I'll multiply those by s's when I need to. Yeah, thanks for spotting that. So I'm just writing down the polynomial for the numerator here. So I've got minus 2s cubed. Then I'm going to have plenty of s's around. Or look for the s squareds now. So I get a minus 10s squared from this part here. But when I bring this first fraction to over s squared, I'm going to get plus 15s squared. So I get 15s squared minus 10s squared. 15 minus 10, so that should give me plus 5s squared. Then look for the s's. How many s's have I got here? I've got minus 2 s's, but then I'll have 9s over here, and I multiply above and below by s to bring this to denominator to s squared. So minus 2 plus 9 gives me plus 7s. And then constant term comes from the 5 times 2, gives a 10, or a minus 10. Whew. Okie dokie. So now I can just divide across by this first polynomial here. Now you see the way I've got a minus sign in the leading term here and a minus sign in the leading term there. Well, I'll divide above and below by minus 1, or multiply above and below by minus 1 just to standardize those. So I can say that y bar now, on the denominator I've got s squared into s squared minus 6s plus 5. So I'm changing all the signs. And on the numerator, I will have 2s cubed minus 5s squared minus 7s plus 10. So this is very good. This looks like progress. We've now solved this equation for y bar. So in principle now we just have to take the inverse transform to get the solution for y of t. We'll just progress. We'll keep going with y bar here. I mean, you could at this stage return to the system and substitute in this value for y bar in here and get an expression for x bar. You could do that at the moment, but I just want to kind of forge ahead with the y bar that we have and go and solve for that. So really, we just have to take inverse transforms. But looking at this, okay, this right-hand side is still it's a complicated rational function. You won't find that function itself directly on the table of transforms. So we'll need to get the partial fraction expansion of this. Okay. So we'll seek the partial fraction expansion of this. Can we factorize this other factor down here? Yeah, it'll be s minus 5 times s minus 1. On the top, we've got 2s cubed minus 5s squared minus 7s plus 10. Now, before we launch into partial fraction expansions, because there's potentially going to be 4 terms in the partial fraction expansion, so I'll need 2 for the s squared and 1 each for the s minus 1 and the s minus 5. But just looking at these roots here, 5, 1, and 0, I should just check the numerator and see if there's any divisibility that will simplify that here. You see, yeah, there is, because when you got minus 5 minus 7 gives you minus 12, then you got a plus 12 when you add the 2 and the 10. So when evaluated at 1, 1 is also a root of the numerator polynomial. And 1 is one of the roots of the denominator. So that factor of s minus 1, we should be able to divide that out from the top and bottom. Okay. So we can cancel the s minus 1 factor to get y bar. So that simplifies the denominator. It's now s squared times s minus 5. And then we're cancelling. So we're going to get a quadratic on the top. It still has to have 2s squared in it. So we're dividing this top polynomial by s minus 1. So you think about, so I'm doing that quickly by thinking of the quadratic I need to have, so that when you multiply it by s minus 1, you get back to that. So I'll need a leading term of 2s squared. And the constant term you can write down straight away. Well, if I multiply this constant term here by minus 1, I have to get plus 10. So that means the constant term has to be minus 10. And then you just need to solve a couple of linear equations to figure out what the s term should be. So what should the s term be? Well, we're going to get 2s squared, and then to end up with minus 5s squared, the s term should be minus 3s, shouldn't it? Yeah, minus 3s. Okay, so now we've got our cubic denominator, quadratic numerator, so we can go for the partial fraction expansion there. 5 is not a root of the, I think it is, no, 5 is not a root of the, what is it? 2s squared, 2 times, no, it's not. It is not a root of the numerator, so there's no more cancelling to be done. So we can go now for the partial fraction expansion. So y bar should look like, it's going to be an a over s plus a b over s squared plus c over s minus 5. Those are the 3 terms that are going to appear in the partial fraction expansion. Everybody okay up to here? Any clarification needed, or do shout out and stop me if you do. Yeah, question.
How were you able to tell that s minus 1 would be a factor?
Well, I just did a quick check. So just checking each of the roots down here, the 5, the 1, and the 0. Just checking were any of those a root of the numerator polynomial. So, well, putting in 5 here, you get 2 times 125 minus 5 times 50. No, that doesn't look like it's going to come out to 0. Now, evaluating a polynomial at 1 is very easy. You just add all the coefficients, because each of the power terms is always 1. So adding those coefficients there, 2 minus 5 is minus 3, minus 7 is minus 10, and then you got the plus 10 at the end. So that told me that 1 was. Okay, any other points to clarify? Okay, so that's our setup for the partial fraction expansion. Yeah, we can do this by hand. Shouldn't use a computer or that. We can do this by hand fairly easily. So you multiply it all together again. So you're going to have an A times S minus 5. You're going to have a B times S minus 5. And you're going to have a C times S squared. So that's multiplying, that's over S squared times S minus 5 again. So then you expand out the polynomial at the top. Now just be careful, we've got S's and 5s, so they look a little bit similar, so just be careful to distinguish those when you've got those around. So there's a factor S minus 5 in here. So you multiply out the numerator polynomial. So what multiplying S squared, what have we got? We've got A plus C multiplying S squared. Then you look for S's, and you see you got minus 5A plus a B multiplying S. Isn't that all? Yeah. And then looking for a constant term, you just got minus 5B. So it's this polynomial, and this we're comparing back to this original expression for y bar. Originally we had y bar as polynomial over s squared times s minus 5, and now again we have y bar as polynomial over s squared times s minus 5. So the only way those two expressions can be equal is if their numerators are equal. The numerators are both quadratic polynomials in S. The only way two quadratic polynomials can be equal is if they have equal corresponding coefficients. So this is going to give me the conclusion about what A, B, and C should be. Now, where should we start? Well, let's start with the B, because the B is the only thing involved in the constant, so we'll be able to get this straight away. So this implies that minus 5 times B equals minus 10. So in other words, B is equal to 2. Then we'll look at the S term, because that involves B, which we know now, so that will determine what the A should be. This also, so comparing S coefficients, you get minus 5A plus B equals minus 3. So you've already got minus 2 there. Equals minus 3. So when you put in B equals 2, B equals 2, so you get a plus 2 on the left-hand side, so you're going to get a minus 5 on the right-hand side, and you bring it over. So yeah, A has to be 1. So, and then we know A plus C has to be 2. And A is 1, so that means C has to be 1. Okay, so the solution falls out there nice enough to that system of linear equations. I mean, if the equations don't work out particularly nicely, if there's A, B's, and C's and all the coefficients, we can always have recourse to Gaussian elimination. We always have that algorithm that will solve the system for us. We use that matrix reduction algorithm to solve the system. If the system is, if it doesn't give up its solution relatively easily, like that one just did. So now we know the A, the B, and the C. So we have this nice expression here for y bar, which we can write out now. So y bar can be expressed expressed as y bar is a over s, so 1 over s plus b over s squared plus 2 over s squared plus 1 over s minus 5. So this is our kind of final solution for y bar, and it's ready and waiting to have its inverse transform taken, okay? Because we have it as a linear combination of 3 functions of s, each of which is contained on the table of Laplace transforms. Okay? Taking the inverse Laplace transform now, we will get, well, when we take the inverse Laplace transform of the unknown function y bar is just representing the transform of y. You take that inverse transform, you get back to the original function y of t. 1 over s is the transform of the constant 1, so you get a constant 1. 2 over s squared is the transform of the function t, so you get a term t. And 1 over s minus 5 is the transform of the exponential function e to the 5t. So finally there, after all that work, we get 1/2 of the solution of the original problem. Remember, the original problem was a system of ODEs in the 2 unknown variables x bar and y bar. So we found one of them there. Okay. So this is half the solution. Now, if we proceed carefully, it might not take us the same amount of work again to get the other half of the solution. But any questions just on our progress up to there? Yeah.
Question on the compute.
Possibly. Yeah, 2 over, yeah, because it's factorial of, yes, when you compare it to the table, yeah, 2t. Thank you. I've just not had enough coffee this morning. Too many little slips. But see, I didn't actually look at the table. I just tried to remember. But, yeah, thank you. Any other little clarifications? Okay, now, so where can we get the x of t from? Let's just look back a little bit carefully. I mean, where did we last see an x? We haven't seen an x for a while. We have to go all the way back to our a and b equations. Remember our a and b equations here? These have an x bar in them. They also have the y bar in them, but we now know what y bar is. So one way of proceeding here, we could take one of our expressions for y bar, either the partial fraction expansion one, or the nice compact rational function one, could take either of those expressions and put them back into either a or b, doesn't matter, and that would eliminate the y bar, and we'd just be left with an equation featuring x bar, which we could then, but then we'd probably have to take further partial fraction expansions to find the x bar. But so that would be one way to proceed. That's kind of maybe the canonical way to proceed, or the algorithmic way to proceed. But if we look back at the differential equations, you see one of the differential equations is quite simple in terms of x. This second differential equation, it only has the term 3x in it. It doesn't have any other derivatives of x. So the other terms here are y and the derivative of y. But we've just identified what the function y of t is. And it's not too complicated. It's 1 plus 2t plus an exponential. So you got y. We can easily work out the derivative of y, and then we'll have 3 times x. We can just divide across by 3. So it looks a much quicker, much more direct route to the solution to take that second ODE and substitute in the function y into that. That kind of looks like, it maybe feels a little bit odd because you're only using one of the equations to obtain the solution to x. So this is a pair of simultaneous equations, so shouldn't we be using both? But No, that's okay, because in order to get to the solution for y, we had to combine the equations. So we took that linear combination of the equations. So we've done the combining of the equations already. So it doesn't feel invalid if we just go to one of the equations now to extract the solution for x. Okay. So to summarize those points I've just made, let me write something to summarize that. So we could return to equation A or B and eliminate y bar now and proceed in a similar way to find x bar. Okay, so I'm just putting down some commentary here to summarize all that thinking I was doing. So we could do that, but that would probably involve more partial fraction expansions and maybe a little bit too much work. So we by considering the original problem carefully, we spotted a more direct way. However, the second ODE is simple in terms of x. It's just 3x is the only x term in it. So instead we use that. So that equation is the dy dt plus 3x plus y equals 2t. So we have this function y up here. We can take its derivative without any trouble. Its derivative will be 2 plus 5e to the 5t. 3x is there, plus y, but y is just all that, 1 plus 2t plus e to the 5t. And then you got your 2t on the right-hand side. So there now is a nice equation just involving x. So just chuck everything else over to the other side, and we should get x of t. So there's going to be a constant there. So what's the constant? It's 2 plus 1. So the constant is 3 on the left-hand side. When you put it over the other side, it's minus 3, and then we're going to divide everything by 3. So you've got a constant minus 1 on the right-hand side, it looks like. There's some t's floating around. You've got a 2t on the left-hand side, but also a 2t on the right-hand side. So that disappears in a puff of smoke. Then you've got these exponentials. You've got 5e to the 5t and e to the 5t. So you've got 6e to the 5t on the left. Put it over the other side. It's minus 6 divided by 3. It's minus 2e to the 5t. Which I believe is correct. So that's the other half of the solution. So you can see there that without any real significant change, we were able to apply that same four-step process using the Laplace transform to solve that system of coupled ODEs. Now, if you're doing another example and it doesn't turn out that you have this quick, direct way to the solution for x of t by considering one of the original ODEs, if the original ODEs are both kind of complicated in terms of x, then I think probably the best way would be to do this, what's indicated here, this first paragraph. Go back to your simplified transformed equations, which we called A and B, and take your solution for whichever variable you solve first, substitute that in, and then you'll just get an equation involving the other variable, and then you go through the procedure again to take its inverse transform. Okay. But just that may involve taking some inverse partial fraction expansions. So just before we finish, so that was a nice example, a good workout with all of that. Any further clarification or any points you want to comment on before we move on from it? Okay, just a little point which I think I skipped over. The scans of these pages I'll put up on the lecture recording as normal in the comments to the video. Yeah, dealing with irreducible quadratic factors. So sometimes when you're doing this procedure to solve these equations, when you do the partial fraction expansion, sometimes we run up against irreducible quadratic factors. So things that won't simplify to a sum of functions with linear factors in the denominator. So there's a little example there, and I've got another one here somewhere on the page here. Yeah, here we go. So in order to deal with these, we need to do a completing the square type operation. So here's another example. So this is dealing with irreducible quadratic factors. So suppose x bar of s is this function, 3s minus 1 over s squared plus 6s plus 13. So this is something which you might encounter after you've done the partial fraction expansion. You might get a term like this. Okay. Now that denominator is irreducible over the reals. When you work out its discriminant, b squared minus 4ac, b squared is 36, minus 4ac is minus 4 times 13. So that's a negative discriminant. So it doesn't have any real roots. So you can't factorize this over the reals. Well, your first point of call is to look at the table of Laplace transforms. So where are functions which have a quadratic in the denominator? A full quadratic, which isn't just a straight square. Well, you see they're all here down the bottom of the table, down the bottom of the first page. There are some quadratics up here, but they don't have any s terms in them, just a square term and a constant term. These ones down here are the ones with kind of full quadratics, but the denominators are always presented in this alternative form, as a square of a linear factor plus an extra constant, or minus an extra constant. This is sometimes called a kind of completing the square form. You have a square and then you complete it to get the original denominator. So what we've got on the page there is going to be some mixture of those. So we have to rewrite our denominator in that form. So you complete the square in the denominator. So we're just getting an alternative expression for this. So completing the square means writing that s squared plus 6s plus 13 as a square plus or minus an adjusting constant. Well, it's going to be a square. You've got s squared there, so it's going to be s. So what do you square in order to get s squared plus 6s? Well, you have to square s plus 3, don't you? If you square s plus 3, you get s squared plus 6s. Of course, you also get a 9, but we want a 13, so we have to adjust it by adding on 4. But when you look at the table, the adjusted constants are always expressed as a square themselves, so we'll write that 4 as 2 squared. So in the notation of the table, this is my a, and this is my omega squared. Okay, so now that's set up for taking the transform of it. Although you'll see we just have to do another little bit of adjusting to it We've got an s and a constant. So if you want an s in the numerator, you have to have it as s plus a. So we have to have it as this s plus 3. So we can have s plus 3 in the numerator, and have s plus 3 all squared plus 2 squared there. Now it's a 3s really, so we have to have a coefficient of 3 in front of it. So this construction, 3 times this will give us 3s. Of course, it'll also give us plus 9, but we need minus 1. So we have to have a minus 10 subtracted from it. So I'll want to write down here a minus 10 over s plus 3 squared plus 4. But when you look to the table, when you have constant over that irreducible quadratic, it's always the constant omega. So I need a minus 10 here, but omega is 2. So I'm going to express that as minus 5 times 2 over s plus 3 all of it squared plus 2 squared. Now normally you wouldn't take a fraction like this and write it as a linear combination like that, because it's too long-winded. This is a much more compact, tidier presentation of it. But the reason we're doing it is that now I see x bar as a linear combination of functions which I can find on the table. Okay? So this here and this here, these are on the table. So I can simply read off their inverse Laplace transforms to get the function x of t. Okay? So taking the inverse transform now, the function x of t will be 3 times whatever the inverse transform of that is. So s plus, that's e to the minus 3t, e to the minus 3t times cosine of omega t. So cosine of 2t. And then this one is minus 5 times e to the minus 3t again times sine of 2t. So that's our function x of t there. You could maybe tidy it up one step further by taking out the exponential. Okay, so that's an illustration of a step you may need to go through when solving these ODEs if you encounter those irreducible, fully complete quadratic factors in the denominator. You have to go through that, completing the square process, and separate it out as a linear combination of functions that are on the table. Okay? Okay, we'll finish it there for this morning. So there's some more exercises open up to you there. There's exercises, the next set of exercises on systems of ODEs. So we can be working on those for the tutorials. I'll be seeing you on Friday, I believe. No, maybe I won't.